Okay, section 5.6. We did something kind of similar to this back in section 5.5. In section 5.5, I might have given you some data, and from the data, I might have asked you to find an equation of the line. And what we did back in section 5.5 is we might have picked two of the points. We might have picked the first one and the last one and used those 2 points to find an equation of a line. That equation that we found is pretty good, but not the best one we can find. So what we're going to do today in section 5.6 is we're going to do what's called modeling. And what modeling means is starting with data, and from the data you want to try to find an equation that matches that data. Why would you want to find an equation that matches that data? Because then you can use the equation to make predictions, and that's exactly what we're going to do. Okay? So this whole process is using linear models to make estimations and predictions. All right, so let's see. The data we have says the percentage of Americans who always wear seatbelts for various years is given below. So in 1992, 70% of Americans wore their seatbelt. 2004, for example, 83%. 2011, 91%. Okay, so first it says, let P equal f of t be the percentage of Americans who always wear seatbelts at t years since 1990. Part A, use a graphing calculator to draw a scattergram of the data. So that was the question that we didn't get to the other day about how to use our calculator. All right, the first thing we need to do, first off, I notice it says t is the years since 1990. So what's 1992 going to be? That's going to be year 2. So when we go to use our calculator, we're not actually going to use 1992, 1996, so on and so forth. We're going to use 1992 is 2. And so 96 would be 6, and 2000, 10, 14, 18, 21. So those are the numbers that we're going to use when we draw our scatter plot. So we're going to draw a scatter plot like so. We're going to do it on our calculator in just a second here. But again, we would scale it maybe going 5, 10, 15, 20. We wouldn't go 1992, 1996, so on and so forth. All right, so how do you do that on your calculator? How do you get your calculator to draw a scatter plot? Anybody know? All right, the first thing you're going to do is you're going to go to y equals. And you're going to clear anything that you have typed in there. We don't want those equations anymore. Those were for a different problem. We don't need them. So we clear those out. Second thing you need to do is you need to type in the data. And you type in the data. I went second quit to get out of that. Let's go back to the home screen. To type in the data, you push the statistics button, which is right here in the middle. STAT, stat, edit. And you should see list 1 and list 2. And list 3 comes up also. We're going to type our data into list 1 and list 2. So I got a bunch of stuff typed in list 1 right now. I don't want that. I want to get rid of it. So what I'm going to do is I'm going to go over to list 1. I'm going to go up to the top, and I'm going to hit clear, and then enter. And that deletes list 1. Now, a common mistake students make here is they hit the delete button. If you hit the delete button, it's really going to delete the list. So not only will it clear it all out, list 1 will disappear altogether. Now that can be fixed. If you make that mistake, let me know. If your list 1 and list 2 aren't showing up, let me know. We can fix it. But in general, you want to go clear, enter to get rid of all of it. Okay, so now we type in our data. So for L1, I'm going to type in the years. That was 2, 6, 10, 14, 18, and 18 and 21. So I just type in each number, hit enter after the number, and I'm going to go over to L2 and type that in. 70, 75, 79, 83, 87, and 91. Yes?
My calculator looks nothing like yours.
Your calculator looks nothing like mine.
No business names, ops, math.
You hit second and then the stat button right now.
No, I hit the stat and that's what it popped up.
Hit stat and then hit enter for edit. Okay? Anybody else have problems with the calculator? Okay, so far, it shouldn't matter if you have a TI-83 or a TI-84, everything should work the same. Some things are going to work different here in a few minutes, so I'm going to go ahead and I'm going to type my data in again, but I'm going to type it into this other calculator. So once again, just to do that, first I go to y equals, make sure I erase anything that's in there. I go to stat, edit, there's junk in here, I clear it out, clear enter, clear enter. 2, 6, 10, 14, 18, and 21. And over there, 70, 75, 79, 83, 87, and finally 91. Okay, so now I have my data typed in. Now I'm ready to make my calculator draw a picture for me. What I need to do is I need to go second y equals. Second y equals goes into the statistical plot menu. So it's called stat plot, statistical plot. Statistical plot. I'm having trouble saying that today. Second y equals. And you should have a screen that looks like this. We're going to hit enter. We're going to turn the plot on. Now we have lots of choices for plots. The one we want is actually the very first one. The very first one is scatter plot. So I'm going to go down to that one and I'm going to hit enter. What's the second one? Anybody know? Let's go to line plot. What's the difference between a scatter plot and a line plot? This one will draw the scatter plot and then it'll connect the dots with lines. So it'll look like something that you see like when you look at a stock market report. How about the next one? Bar graph, properly called a histogram. And then, if you've had some statistics, you might know those two. Those are stem and plot, or stem and whisker graphs, they call those. The last one, truthfully, I don't know what the last one is. Okay, so anyway, we turn our stat plot on. We make sure we have the first one. We make sure our x's are L1, our y's are L2. And then we have three choices. We can use little dots, we can use little plus signs, and we can use little boxes. Personally, I like the little boxes because I have trouble seeing the little dots. Sometimes my calculator screen is dirty and the dirt looks like little dots on my screen, so I like the boxes. Okay, last thing you have to do. If I hit the graph button, you'll notice nothing shows up. Once again, I almost never hit the graph button, but I hit it anyway. What you want to do now is hit the zoom button, and you want to go down to number 9, which is zoom statistics. And the calculator will figure out a nice window for you to look at your statistics. So there it is. There's our data. Questions on that? All right, so again, let me set that up on my other calculator here. Go to y equals. Okay, I already cleared those things out. Second stat plot, turn it on. Scattergram, L1, L2, little boxes, all looks good. Zoom, number 9. Okay, so we've answered part A at this point. Use a graphing calculator to draw a scattergram of the data. There it is. Why would you take the time to draw a scattergram before you go ahead and find the equation?
To see which points it does.
Not really, but sort of. Yes?
To see if it's actually, to make sure it's not running.
Yeah, you need to look at the data and decide which kind of equation makes sense. Looking at that data, that equation, an equation that looks like it would make sense would be a line. But does all data fall into a nice straight line?
No.
No. So later on in this course, we'll study graphs called parabolas. So maybe we'll look at data that falls into the shape of a parabola, and we would use a different kind of equation. Or we'll also look at exponential functions. And then our data would look different, and we would use a different kind of equation. So you have to draw the data to see what makes sense. In this case, I do think a line makes a lot of sense. All right, now, there's a technique on the calculator for finding the line that comes closest to hitting all of the spots. And the technique on the calculator is called a regression. To get the regression, and this is where the calculators get different. So I'm going to do it first on my TI-84. This TI-84 has a newer operating system, and then I'll do it on my TI-83 for those of you who have older calculators, because it will look slightly different. All right, to find the equation of the line, you're going to push this stat button again, S-T-A-T. You're going to go over to calculate. And you're going to go down to number 4, which is linear regression. LINR, linear regression. And they use AX plus B. I really, really wish they would have used MX plus B, because that's the way we usually write it in a math class. But they didn't. They used A. That's their choice. I'm going to hit enter. Now it asks me some questions. Is my X list in L1? Yes. Is my Y list in L2? Frequency list. Don't worry about that. Store a regression equation. Don't worry about that. Move down, down, down to where it says calculate, and hit enter. So there's my answer. Y equals, let's see, I'm going to round off to a couple of decimal points here. Y equals 1.073x, because that's the A number, plus 68.138. Yes?
When I hit enter, why doesn't it come up with A equals? Well, I did it twice.
Okay. You have the older type calculator. So hit clear on your calculator. And now we're going to start over. We're going to do it again. For those who have the older type calculator, it looks like this. You go stat. You go over to calculate. You go down, down, down to linear regression. You hit enter. And it just writes linear regression. It looks like it didn't do anything. All you do now is you hit enter again. And your calculator assumes that you put your x's in L1 and you put your y's in L2. If you didn't put your x's in L1 and you didn't put your y's in L2, you'd have to tell the calculator otherwise. So my suggestion is always put your x's in L1 and always put your y's in L2, and then it's a lot easier. Okay? So we got the exact same answer, didn't we? Didn't matter what kind of calculator we used. That's good. Questions so far? Now, the only thing I should do, again, if I'm doing my homework on the computer, doing it online to earn that extra credit, I noticed that it told me I shouldn't be using X and Y. What letters should I be using?
P and T.
I should be using P and T, or I could use F and T, depending on my choice. I'm going to go ahead and use P and T, so I should have P equals 1.073T plus 68.138. And again, the computer is very, very fussy about that. Yes?
If we're doing homework, we just put let P equal Y.
If you're doing that on a quiz or on a test, I would be fine with that. If you're doing it on the computer is only going to accept that answer. If you give it x's and y's at all anywhere, it's going to mark it wrong, because it's not programmed to understand that x equals t and y equals p. Okay? So it's kind of a pain, but you'll get used to it. Okay, then we're asked some questions about this. I'm going to try to make some predictions here. It asks, what is the p-intercept? How do you find the p-intercept?
On the left.
It's like asking for the y-intercept, because p is y. How do you find y-intercept? Set x equal to 0. So if I asked you to find the p-intercept, you plug 0 in for the other letter. That's what p-intercept always means. So this means t equals 0. And when I plug in t equals 0, that's very easy. When I plug in t equals 0, I get 68.138. Then it asks an important question. What does this mean in this situation?
1990
Perfect. Perfect. That's exactly what it means. T equals 0 means the year 1990, because that's when we started, since 1990. So t equals 0 means in 1990, 68% of people wore seatbelts. That's what it means in this situation. In 1990, 68% wore seatbelts. Questions on that? All right. Part D. What is the slope? Slope is m equals 1.073. And then again, what does it mean in this situation?
Each year, the percent of people wearing seatbelts increases by 1.7.
Exactly, very good. What you have to remember here is, how would you find slope? If I told you to pick two of these points, how would you find the slope? You would take y2 minus y1 over x2 minus x1. So that means you have the y's on top. The y's are percent, and you would have t's on bottom, that's years. So this is 1.073% per year. So what this tells you is, this tells you how fast people wearing seatbelt is increasing. So if I'm going to write this in a sentence, the percent of people wearing seatbelts increases 1.073% per year. And how did I know that it was increasing? Because the slope turned out to be a positive number. If the slope was a negative number, I would have said that the number of seatbelts was decreasing. Very good. All right, getting close to the end here. E, what is the t-intercept? All right, well, up above we found the p-intercept. To find the p-intercept, we plugged in t equals 0. Here they're asking for the t-intercept, so what do? I put, if I want the t-intercept, that means I want p to be the number 0. So I have 0 equals 1.073t plus 68.138. So I solve that. I subtract the 68, so minus 68.138 equals 1.073t. I divide, I get t equals negative 68.138 divided by 1.073. Negative 63.5, I'll call it. All right, what does that mean in this situation? Let's see if we got somebody else to answer today. What does that mean? Any thoughts?
Well, I'm kind of confused because T is the year since 1990, so that was an
Okay, so that is a little bit confusing, I agree. T stands for time. And lots of people will tell me time can never be negative. And in this situation, I would disagree with that. What this means is we started in 1990. So what would negative 63 mean? It would mean 63 years before 1990. That's correct. So in this case, I do think time being negative makes sense. So what's 63 years before 1990?
1927.
So in 1927, what happened?
No one's.
Nobody wore seatbelts. How do you know nobody wore seatbelts? Because, well, not because it's a negative number. That told us the time. P was set equal 0. P was the percent of people wearing their seatbelts. So this says, in 1927, nobody wore seatbelts. Do you believe that? Yeah, I believe it.
Wouldn't this be like model breakdown though?
I think you could argue that this is model breakdown. What do you mean by model breakdown?
That the data, we don't have data sufficiently showing that. It's just like a random prediction almost.
Correct. I would agree that this is almost like a random prediction. Look at our data. Our data only spans from year 2 to year 21. Our data really only spans 19 years. Do you think it's a good idea to predict 63 years outside of your data when your data only spans 19 years? No. I don't think you can be very confident that this answer is correct. Okay? Was there a time when the people didn't wear their seatbelts?
Yeah.
Sure, but I'm willing to bet it wasn't 1927. According to our equation says the answer is 1927. I don't think you can trust that answer, though. And that's something you need to recognize. Sometimes just because you can make a prediction doesn't mean it's a good prediction. And you see this sort of thing all the time. The most common one I see is people predicting if you have a child today, how much is it going to cost to send that child to college 20 years from now? There's too many factors. I don't think anybody can accurately predict 20 years into the future. I hope not, because those numbers are scary. If any of you have young children looking 15, 18 years down the line at college expenses, is a very, very scary thing. It's pretty scary looking at it today. But down the line, it's even worse. Okay, so we get an answer. We don't really trust it. But that's okay. That happens sometimes. Sometimes you make bad. All right, let's make some good predictions, I think. Predict the percentage of Americans who wore their seatbelt in 2007. What am I going to do there?
Can you subtract the 1.073 from 87?
From 87. Where'd you get 87?
Because that's in 2008, and it goes, it increases by, 0.053% each year, so it's going to increase that away from
Okay, yes, that's an excellent way to answer it. That's not how I would have done it. Her answer was, if I want to know the seatbelt usage in 2007, I can go look at my chart. I've got 2008, and I know from 2007 to 2008 it went up by about 1%. So a good answer should be about 86%. Yes, that's an excellent answer. That's not how I would have done it. But that's correct. Here's what I would have done. I would have said, I'm starting in 1990. 2007 is how many years away? 17. So I would have said t equals 17, and I would have taken 17 and plugged it into my equation. That's what I would have done. So p equals, both answers are correct. We should get the same answer. So I grab my calculator and I see what I get. 1.073 times 17 plus 68.138. I get 86.4%, we'll call it, which is exactly the same thing you got when you took the 87 and subtracted the 1.073. Next question. Oh, wait, I'm not done with this one yet. Is this an example of interpolation or extrapolation? Anybody know what those big fancy words mean?
It would be interpolation.
It would be interpolation in this case. Why? What does interpolation mean?
If you're using, you're going from the confidence of the data, not going outside.
Exactly. Interpolation means you're within the confines of your data. Was 2007 within the confines of my data? Yeah, because my data started from 1992 and it ended in 2011. So 2007 was inside the data, that's interpolation. So what's extrapolation mean? When you go outside the data. So I think the next question is outside the data. When will 100% of Americans wear their seatbelt? How are you going to figure that out? But P is 100 would be how I would do it. So we would have 100 equals 1.073T plus 68.138. And I would solve that equation. How do you solve? I take 100 and I'm going to subtract the 68.138. And then I have to divide by the slope, divide by 1.073. So we'll call it 30 years. So we predict, in the year 2020, everybody will wear their seatbelts. And in this case, that is extrapolation, because 2020 is outside of the data we were given. Do you believe that? Do you believe that by the year 2020, everybody will wear their seatbelts? No, probably not. But again, that's what our model predicts. Questions on that?